Today we begin our conversation on the Field Effect Transistor, from the JFET to the MOSFET. At the end of this set of slides, I expect that the student can do all these things: model in DC the JFET and the MOSFET, analyze the bias circuits for FETs, but not this FET, not Boba Fett, rather this one, the MOSFET. Identify advantages and disadvantages of the FET versus the BJT, the bipolar junction transistor that we saw previously. Tell the different types of field effect transistors, the JFET, the D MOSFET, and the E MOSFET. We'll use a significant amount of time on the E MOSFET. The behavior of a field effect transistor depends enormously on how a p-n junction that is reverse biased behaves. You don't remember that? Let's refresh your memory. Previously, we began with the study of semiconductor materials. Let's review a little bit of that. From the type P material that has an abundance of positive electric carriers, we called them holes, to type N materials which has an abundance of negative carriers, electrons, abundance of free positive charges and abundance of free moving electrons. By the way, it's not that the P material is positively charged or the N material is negatively charged. No, they are both electrically neutral. What's different is that the P material has free to move positive carriers and the N material has free to move negative carriers. Formerly, we put them together and we formed what we call the p-n junction. The p-n junction was found to have very interesting electric properties. It allowed currents to flow from P to N, but blocked currents that tried to flow backwards through them. They were, in fact, an electric valve. We call that p-n junction a diode. Now let's see how that p-n junction works when we try to pass currents forward through it from P to N. We apply an external resource like so that pushes, if you allow me to use that word, current from P to N. That tries to get current into the P material, which effectively means that it's pulling out electrons out of the left of the P material, and by doing that, it's creating new holes in this region of the material, increasing the density of holes on the left-hand side of the P material. That source at the same time is pulling current from the right of the N material, which is equivalent to saying it's feeding new electrons into the right of the N material, increasing the density of free electrons on this side of the p-n junction. Observe there is a high density of holes on the left of the P material, and there is a high density of electrons on the right of the N material. That gradient of density will move holes towards the right and electrons to the left, and they will join in the center and recombine and disappear. Free electrons and holes, they recombine and they disappear. The motion of holes and electrons is facilitated by the electric field created by the external source. This is the way the p-n junction operates when it's forward biased. That process can continue forever. Now let's apply a backwards bias to the p-n junction. We are trying to take current out of the P material. That is, we're trying to feed electrons on the left of the P material. If we do that, those electrons will recombine with some holes on the left of the P material, and the density of holes will decrease on this side, on the left-hand side of that. At the same time that we have holes disappearing on this one on the right-hand side of the p-n junction, that attempt of the external source to feed new current into the end material will be materialized by an extraction of electrons, which will reduce the density of electrons on this part of the p-n junction. That difference of density in holes and electrons will get the holes and electrons move away from the junction to even out the density of carriers in the p-n material bands. When they do that, what they're doing is uncovering some of the fixed charges near the junction, creating a region that is depleted of free charges. So there are no carriers in this zone, and what there is a region that has stationary charges, static charges in there. Negative on the P side and positive on the N side. What happens then is that those stationary charges there will counter the external V source and will stop the flow of carriers. In fact, will cut the current. If we increase the voltage of the external source, the process will go on for a few nanoseconds, increasing the width of the depletion zone until it's big enough to counter the increased externally applied backward voltage. We apply a larger voltage source, and what we get is a wider depletion zone. Let's summarize that. The point of all of this conversation is that when we have a p-n junction that is reverse biased, it develops a depletion zone, which is a zone that is wider the higher the voltage we apply backwards to that junction. The depletion zone has no free charges. The depletion zone instead has fixed space charges, charges that are fixed and trapped in the crystal of the material. There is no current through a reverse biased junction. Formerly, we introduced the BJT, the bipolar junction transistor, as a hamburger with 3 terminals E, B, C. We consider that the P material is the meat patty and the N-type materials are buns. Then we have the emitter, the base, and the collector. Well, today we introduce a different type of semiconductor sandwich, one that looks more like a hot dog than a burger, something like this. The winner will be a slice of N-type material surrounded by 2 slices of P material. I know what you're thinking. What you're thinking is, what you've done is just take a PNP regular transistor and draw it sidewise. Well, yeah, it can be seen that way. However, look at the terminals we will connect to this device. We'll connect a terminal at the top, we'll call that the drain, a terminal at the bottom, the source, and we'll join both P slices like so and connect that to a third terminal, the gate. If we apply an external V source between the drain and the source, a current IDS will flow from the drain through the source. This is like a big resistor between the drain and the source anyway. We call this part of the new device the channel. Now the names drain and source. Well, it's so because the current flowing from the top actually is equivalent to electrons being originated at the source and disappearing at the drain. So the source is a source of electrons and the drain is a drain of electrons of the device. A source of electrons and a drain of electrons. We observe that what we have is a resistor. The higher the voltage VDS we apply here between the drain and the source, the more current we get flowing from the drain to the source. They are proportional. They have a resistance that is given by the inverse of the slope. Now, what happens if we apply also a voltage between the gate and the source? What we're doing with this upside down voltage source actually is ensuring that the PN junction between this side and the channel is reversed biased. When we do that, you know that this PN junction will develop a depletion zone. Reverse bias PN will create a depletion zone. But when we have a depletion zone, the actual effective cross-section area of the channel for current will be reduced. In other words, the resistance of the device between the drain and the source will be higher. The more negative the gate is with respect to the source, the narrower the channel, the higher the resistance, and the smaller the current IDS will be for a given value of voltage VDS. A depletion zone appears, a narrower channel, more resistance between the drain and the source. More voltage, narrower channel. That's right. Even more reverse voltage, even narrower. If we increase the VGS voltage to a point, it will cancel out the channel. We say the channel has been pinched off. We call that specific value of the VGS the pinch off of voltage of the channel, or the VGS off value of voltage of the gate source. That is an important parameter in this new device. We are specifying the VGS off. How much reverse voltage we need to apply between the gate and the source to cut the current in the channel. When the voltage VGS is 0, that is, when we have connected the gate to the source directly, we have a certain resistance between the drain and the source given by the inverse of this slope. When we increase the negative voltage of Vs, let's say to half of a volt, then the resistance is higher and higher and higher. If we get VGS to be equal to the VGS off of voltage, you know what's going to happen. The current is 0, and this slanted line will be now horizontal. What we've created is a variable resistor between the drain and the source that is controlled by the voltage between the gate and the source. Now consider the scenario in which the voltage VGS is even equal or more negative than VGS off, the voltage necessary to pinch off the channel. If that is so, we will have the channel cut off, pinched off. We say that device is in cutoff because the current between the drain and the source is 0 amps. That is the specification for such a device in cutoff mode. Make sure that the voltage VGS is less or equal to VGS off. With that polarity, the current IDS will be 0 and the device will be in cutoff mode. Now what happens when the voltage VGS, this one, is above the pinch-off voltage VGS off? Well, in that case, the depletion zone will not be collapsing the channel. No, there will be a current IDS that will flow from the drain to the source. But as it flows down, that current will produce a voltage drop along the channel. At the top, the voltage will be higher and will be reduced itself slowly all the way to the top where the voltage is, the reference one, is 0 volts. Well, what that is telling us is then that the junction PN will be more heavily reversed biased at the top and less at the bottom. That means the depletion zone is going to be wider at the top and lower at the bottom. Absolutely. So the depletion zone, actually, when there is current IDS, will have that shape, a conical shape. But what I'm telling you, you say, is what that the resistance of the channel not only depends on VGS, it also depends on VDS. The more VDS, the more current, the more drastic this reduction of the channel's width will be. Well, let's define a voltage. The overdrive voltage, how much higher VGS than the critical pinch of voltage VGS off. This voltage here, this one, VGS minus VGS off. That is the margin of safety for that. But that is when there is no current from the drain to the source. That is the overdrive voltage. What happens if we increase VDS more and more and more until that voltage is exactly that margin, that overdrive voltage, that VGS minus VGS off? Let's see what happens. I'm going to show you that at point the voltage between the gate and the drain will be exactly the pinch of voltage, and there will be no channel up here at the top. Let's compute the voltage VGD. How much higher the gate is than the drain. We use KVL. Well, to find how much higher the gate is than the drain, let's find how much higher the gate is than the source, VGS, and how much higher the drain is than the source, VGD. VGS minus VDS should be VGD, how much higher the gate is than the drain. But we know that VGDS is the overdrive voltage. We substitute there and get that VGD is VGS pinch off. That is the voltage between this P material here and the drain material here is exactly the pinch of voltage, and in that case there will be no channel near the top. And then we ask ourselves, does it mean that when this voltage VDS reaches the overdrive voltage VGS minus V pinch off, the channel shuts off near the top and there is no current? No, not really. You see, the current will not stop flowing in this situation because this point A continues to have the same voltage it had with respect to the source, and according to Ohm's law, there will continue to be a current flowing between A and the source. The point will be located at the same point approximately and at the same voltage, regardless of how much more voltage we increase VDS. Or when VDS rises above that overdrive voltage, the current remains constant. Let's write it. If VDS, this one, is above or equal, greater or equal than the overdrive voltage, the current drain source is constant. And other figures, we say when that happens that the transistor has reached saturation. We have saturated the channel. Well, that is before saturation, when VDS is less than the overdrive voltage. And then when VDS is exactly the overdrive voltage, P appears. And then when we increase VDS above the overdrive voltage, the depletion zone grows towards the drain, but A remains approximately in the same point and at the same voltage difference with respect to the source, and the drain current remains constant. Nowadays, we call that pinch of voltage the gate source voltage that cuts off the channel current. We prefer to call that pinch of voltage VGS off. If VGS is below or equal to VGS off, there is no current in the channel, regardless of how much voltage we apply between the drain and the source. The transistor is in cutoff mode. Now, if VGS is above the VGS off, the pinch off voltage, well, there is going to be a current in the channel, assuming there is a VDS voltage. You see, there's going to be a current in this channel if there is a VDS voltage. How much current? Well, it depends on how much voltage we apply VDS between the drain and the source. Absolutely. Let's define what is the overdrive voltage. Is this one. How much higher VGS is than the pinch off voltage, V overdrive. And we've said if VDS, the drain source voltage, is below the overdrive, then the transistor behaves as a variable resistor. We say the transistor is in triode mode between the drain and the source. In that zone of operation, we also call that the ohmic zone of operation, the relationship between current in the drain and the voltage we apply between drain and the source is approximately linear, at least for small values of the current. This current here. And the more voltage we apply between drain and source, the more current we have between the drain and the source. But if we make VGS more and more negative, then for the same VDS, the voltage will get less current. The resistance increases. If we increase the negative value of VGS, eventually we'll get a pinch of voltage, and this line will be completely horizontal, and we have in cutoff mode. But up here, the transistor is in the triode mode of operation, behaves as a variable resistor, as a resistor controlled by the VGS voltage. That is true as long as VDS stays below the overdrive voltage, that safety margin above the pinch of voltage of the V gate source voltage source. What happens if we increase VDS above that overdrive voltage? This is what happens. When we increase this voltage VDS above that critical value, this one is the overdrive voltage, then the current becomes constant and independent of VDS. We say that is the saturation current of the transistor. If that voltage of the gate source is 0, then that constant value will be called the drain to source saturation current, and that's going to be a characteristic of the transistor that the manufacturer will include in the data sheets. For different values of the VGS voltage, we have different curves. Down here we have the cutoff mode when VGS is VGS cutoff. This distance here between the dashed parabola and the vertical axis is the overdrive voltage for different VGS values. Please observe that what we assume to be straight lines in the triode or variable resistor zone actually are half parabolas. You see, this is half a parabola all the way here, and so are these and that. The boundary between the triode mode and the saturation mode is also a parabola. We will see that soon enough. But now when we are in saturation mode, the relationship between the current in the drain and the voltage VDS will be none. There will be a relationship, however, between that current in the drain and the voltage between the gate and the source. That dependence is given by this quadratic expression. IDSS is a constant, depends on the transistor. And the VGS pinch-off is a constant that also depends on the transistor. So you see that current depends only on the gate source voltage. But that relationship is quadratic, not linear. This is true as long as VDS is greater or equal than the overdrive voltage. We call this the saturation mode of operation, which is where the transistor amplifies signals input at the gate. We need a symbol for this transistor. This is going to be a symbol. We identify the gate, the source, and the drain. Well, there are other symbols for this transistor. I invite you to pause the video and look at each one of them carefully. But this is the favorite one in many textbooks and in industry as well. We need to identify their currents and voltages, in particular the drain current. And because the gate current is always 0, this PN junction is going to be reverse biased after all, then the source current is going to be the same drain current. We also need to know how much higher the drain is than the source. We need VDS, and we need to know how much higher the gate is than the source, VGS, which in normal operation is going to be negative. The symbol we'll use will be this, and the model that we will identify as representing that behavior is this one on the right. This gap implies zero gate current, and this control current source tells us that the drain current is controlled. Controlled by what? Controlled by this voltage VGS. We know that in the previous transistor, in the BJT, the collector current was linearly dependent on the base current. But in this transistor, in the JFET, the drain current depends on the gate to source voltage, this voltage here. However, that dependence is quadratic. Amplification in the JFET is not linear, it is quadratic. So that JFET introduces a little bit of distortion. That's an argument to use very little oscillations in the input signal to that transistor. Tutorial time. Biasing the transistor, that is, guaranteeing that the transistor is operating in its saturation zone, in its saturation mode, so that it works as an amplifier. The transistor is characterized by its IDSS current, 12 milliamps for this particular one, and also by the pinch-off voltage, VGS, pinch-off negative 3 volts. We want to solve that circuit. Allow me to assume the transistor is in saturation mode. That is why I have that bias circuit. Well, we will compute the drain current as this expression, assuming that the transistor is in saturation mode. You say, well, it's in saturation if two conditions apply. That VGS is above the pinch-off voltage, that's right, and also that VDS is above the overdrive voltage. That is a condition. You say, who was the overdrive voltage? Was how much higher VGS was than the pinch-off voltage. How much higher this voltage is than the pinch-off voltage? Well, we need to compute VGS. That's right, and we need to compute VDS, and we need to find out ID. Let's do all of that. You say, we begin with this. Let's compute VGS, this voltage. For that, I'll need VG and VS. Well, VG is how much higher the gate is than the reference node. Okay, it's easy to compute because the current in the gate is 0. We have a perfect voltage divider of 15 volts among those two resistors, 750 and 150 kilos. So VG is given by a voltage divider 15 volts times 150 divided the sum 150 plus 750, that is 2.5 volts. The gate is 2.5 volts above the reference node. How much VS in this one? How much higher is the source than the reference? Well, that's given by Ohm's law. You see, if I multiply 1,000 ohms times ID, I get the voltage VS, 1,000 times ID. That means that VGS, that I'll need in this expression here, is 2.5 volts minus 1,000 ID. If I substitute that here in this expression, I can write it again. IDSS is 12 milliamps. I'm going to write that with integers like that. Multiplies 1 minus VGS, that is 2.5, minus 1,000 ID divided by VGS, pinch off negative 3 volts down here. This is a quadratic equation with only one unknown, the drain current. We solve it, quadratic, all right, and we find that current would have to be 3.8 milliamps if it's true that this transistor is in saturation. How was that? We demonstrated the transistor is really in saturation. Well, for one, we can compute VDS, this voltage. That voltage is going to be 15 volts, the whole voltage from the top to the bottom, minus a drop in the 1.5 kilos and 1000 ohm resistors. You say, okay, that voltage, VDS, is going to be 15 minus 1500 and multiplies 3.8 milliamps minus 1000 times 3.8 milliamps. The voltage is 5.5 volts. VDS is 5.5 volts approximately. Well, we need also the overdrive voltage to compare. Well, let's compute the overdrive voltage, VGS. Well, VGS is, we agreed, 2.5 minus 1000 ID. That is going to be VGS. Well, VGS is going to be 1.3 negative. Compute it. 2.5 minus 1000 ID, that is minus 3.8 volts. 2.5 minus 3.8 volts, that is negative 1.3 volts. Minus 3 volts, that is 1.6 volts, that is the overdrive voltage. VDS, which is 5.5, is more than 1.6 the overdrive voltage, and that means the transistor is indeed in saturation mode. That quadratic expression is valid, and those numerical values are correct. The drain current is 3.8 milliamps. VDS is 5.5 volts. And that is all for this one. In the next video, we will visit in detail the MOSFET. That is all for now. Thank you very much.